In today's lesson, we're going to look at how we sketch piecewise functions, sometimes called hybrid functions. But in other words, what we're saying is, how do we sketch a function which is made up by many different functions like this? And the first thing that we need to have a look at is their respective domains. So I want to imagine that this one is just in blue, we might do this one in black, we might do that one in green. So effectively, whenever we're looking to sketch these types of functions, we need to imagine their domain, we sketch them out in parts, and then join them up, or I suppose start and finish them based on where their domain is. In this case, you'll see this graph here, they'll all be joined up nicely, but that won't always be the case. So let's first see if we can imagine what this domain means, and we'll start with a number line. So we can see up here in our number line that our first function, negative x minus 1, works for everything that x is less than 0. So that's what we're looking at there. So we imagine that we've got this open dot, and it's everything that's to the left as such. We can see that our next function, 2x minus 1, exists between 0 and 1. Now it's inclusive of 0, and it goes up to 1, but that doesn't include the 1. Finally, we can see that half x plus a half has a domain that's from 1 inclusive onwards. So when we can see that we've got a nice solid line, and arrows going to the left and to the right, the complete domain of this hybrid functions is actually just the real number field. So let's have a look at what it's like to sketch this graph. Our first graph is negative x minus 1. So that's a gradient of negative 1, so that'll look something like this. And instead of being at the origin, it's being translated down 1. So negative x minus 1 would normally look like that. We can see that it's got an x-intercept, if we let y equal 0, of minus 1. And we know that we need to stop this when x equals 0, because that's our domain. So everything that exists to the right of that y-axis I'm going to ignore, and we know that it can't include that. The y-intercept in this case, remembering mx plus c, is telling us that it's negative 1. Now our next graph is at 2x minus 1. So that's a graph that would have quite a bit of a steeper positive gradient, so it might look something like this. And it's also dropped down to minus 1. Now we need to start this at 0. So what I'm going to do is say 2 times 0 minus 1 is negative 1, or you might have recognized that from mx plus c. And you can see that this graph starts at the same point that the last one finished. So I can just put it in there. Now, it's a straight line going up, and it's going to end wherever x equals 1. Whoops, sorry about that. So we sub in 1, so this is 2 times 1 minus 1, which gives me the answer 1. So remember, it ends with an open dot wherever x equals 1. Finally, our last graph is half x plus a half. So this time we'd think that it has a slower gradient. And if we're thinking that it begins where x equals 1, we can find the beginning by subbing that in. Half of x, in this case will be 1, plus a half is equal to 1. So our first point, when x equals 1, y equals 1, well again, this joins quite smoothly. So we'll join that up, and we know that it goes onwards. So our critical points here are almost all labelled. The only thing we notice is that we're missing an x-intercept there. Now that belongs to the graph 2x minus 1. So if I let y equal 0, I would say 2x minus 1 equals 0, and x equals a half. So that's at 1/2 and 0. What we're looking for here, we can see that we've got points where they were open dot and then a closed dot at the same point. So we're just going to make these join nice and smoothly now. And the same thing down here. So this is going to go down, and we've got a very sharp change in direction going up. This is going to get to that point, and again a sharp change in direction, looking to make that a nice solid line. So we might just tidy that up. It's really important that we can see that sharp change in direction. It creates what we call a cusp. And it's really important that it's very clear where that changes. Any critical points like x-intercepts, y-intercepts should also always be labelled. Finally, you might think, how on earth do I label this graph? And there's a nice little trick that we can do is we can call this x, we can call this y, and simply state y equals f of x. Now would be a very good time to pause the video and attempt to sketch this graph. What you should be thinking is, let's first visualize the domain. So we're going to make sure that we can read the domain, and I would do that number line just so I can help see it. It's going to tell you if there's anywhere that this function doesn't exist. So read the domain and interpret it as you see fit. Once you've done that, we would look to sketch these individually. So I would look to just sketch these graphs, particularly as they get a little bit more complicated, and rub out the bits that you don't need. Once you've done that, look to make sure of your endpoints. Now, to make sure of your endpoints, that's going to require you to pay really close attention to the domain there, see whether it's less than or equal to. So pause the video, give it a go, and we'll do the solution next. Okay, our first thing to do is to look at the domain. So x is less than -3. So I've got to think here, if I had a number line, and I can just envisage this with my ruler, I might put it at the top here. Here's our number line. We've got 0, 1, 2, 3, -1, -2, -3. That first graph only exists to the left of -3. Then we can see that the parabola, x squared, only exists where x is greater than 0. So these are disjoint. We can see there's not going to be an overlap between these curves. So let's start with the first one. We've got 1 over x plus 3. So that means that there would always be an asymptote at x equals -3, because this is a hyperbola. We'll just fix that screen up. Apologies about that. So the plus 3 means we've got an asymptote at x equals -3. Now, given that there's no plus k, we've also got an asymptote here at y equals 0. So usually I might see a hyperbola that looks something like this. But because I'm only interested in what's to the left of -3, I can rub this section out. We might try and just fix this shape a little bit as well. And there we go. So our next thing is to sketch the parabola. That's just the graph of x squared. Now that would normally look like this. But we know that we're only interested in everything that's to the right of 0. So I'll rub out the bit on the left. Finally, I need to make sure of my endpoint. And because I can see that it's exclusive of that 0, you can see up there in our number line, I need to have a nice open dot. So I'll just make that really clear for the examiner that there's an open dot there. We can go over this a bit smoothly. and this is our hybrid function. Remember that I've called this asymptote y equals 0, so it's really important that we label this x and y, and label the graph that we sketched y equals f of x. Now this next example is very similar to what we've had before. The only difference is you can see sometimes they'll have this word if is here, but you can basically just ignore it and everything's exactly the same. It's a different way of notating exactly the same thing. This is the curve and it exists for this domain. So pause the video, give this a go, and we'll go through the solution in a moment. Okay, first thing that we're going to do is just imagine this domain. So we'll get our ruler out, we'll imagine a number line. I can see the critical numbers here are 0, 2 and 3. So if I think I've got my number line here, I might go 0, 1, 2, 3, 4. Maybe put in a -1 there. Our first graph works for where x is less than or equal to 0. Now that's equal to 0, so I think this curve here is everything to the left of 0 and it's inclusive. My next graph is between 0 and 2, and this doesn't include any of those values. So I might think that the next one is between 0 and 2, and it doesn't include those values. Let's tidy that up. There we go. Finally, our last curve is everything to the right of 3, and it includes 3. So it looks like that. And so you can see here that there's actually going to be a space between 2 and 3 where this function doesn't exist at all. So we're going to see a gap in our function once again. Let's start with our first graph. We've got -x plus 3. Well, the gradient for a negative graph looks like that. The gradient of -1 looks just like this. And it's plus 3. So the y-intercept, or where x is 0, recalling that that's an important piece of information, is going to be 3. So we've got a graph that looks like this. It's inclusive of the point 0, 3, and it goes off to -infinity. Next we've got the parabola x squared plus 3. Well, the parabola x squared just looks like that u. It's between 0 and 2, so once again it's got a y-intercept of 3, because if I subbed in 0 for x squared, I'd have 0 squared plus 3. So this is a parabola that will look like this, and it's going to end at an open point where x equals 2. So if I think what was g of 2, well that's going to be 2 squared plus 3, which is 7. So now I've got this point 2, 7. Lastly, I've got -2x plus 13. So I'll just make that a little bit bigger. -2x plus 13, that starts at the value x equals 3. So if I think what would g of 3 be? Well, -2 times 3 plus 13 is -6 plus 13, which is 7. So it's going to start at the same height, which is here. It's going to be inclusive, but it starts at the value x equals 3. So there's that little purple gap that we were thinking about. This has a gradient of -2, so it's going to be twice as steep as my last one, and it needs to go down. The last critical piece of information will be our x-intercept. So this occurs whenever we let y equal 0. In other words, where does -2x plus 13 equal to 0? And that would be 13 over 2, or 6.5. So we'll just put in 13 over 2 and 0, And we'll label everything appropriately with x, y. This time, y equals g of x, because the function's not f, it's g. The second part of this graph asks us to state the function's range. Now, if we're thinking about the range of this graph, that's a span of all the y values, you can see here that it goes up to infinity. So certainly just the left bit alone includes all the values from 3 to infinity. And here it starts at 7 and it goes down to negative infinity. So the range of this function, we could say ran g, is actually just reals, because it goes all the way up to infinity, down to negative infinity. Not that it's asked for it, but the domain of g, in this case, are all the values except in between 2 and 3. So the domain, we would say, is negative infinity. Let's just fix that up a little bit. Negative infinity to 2, and it can't include 2, or it can include 3 to infinity. Another question that comes up quite often with piecewise or hybrid functions is when we're asked to evaluate. So we're asked to evaluate, let's zoom back in there, at certain points. So when we're asked to evaluate f of negative 1, we need to first think, well, where would that exist? If I look at the domain, the value negative 1 is inclusive here. And so that's going to be put into that function there. Let's just fix that up. If we're asked to find f of 0, well, I know that f of 0 lies between negative 1 and 1. So this is what I'll use to find f of 0. Finally, if we're asked to find f of 4, we're just going to use that function there, because 4 is after 1. So let's start. We know that f of negative 1 is going to be the square root of minus x, in this case minus a negative. And so that's just going to be 1. If we needed to find f of 0, we're not going to use the square root of negative x. We're now going to use 2 minus x squared. So this is going to be 2 minus 0 squared, which of course is just 2. Finally, f of 4 needs to be put into this square root of x plus 1. So f of 4 is equal to the square root of 4 plus 1. Now, we're going to treat this as a positive 2 plus 1, and that will end up being the value 3. There is an argument here that you could say, well, the square root of 4 is both plus or minus 2. But you'll see when we sketch this graph, if it's a square root graph, it looks like that, because it hasn't been reflected anywhere. So the only possible answer would be up here, which is at the value 3. So part B asks us to sketch the graph y equals, and it says brackets f, x, sorry, it should say f of x, my apologies. So we need to sketch this hybrid function. To do that, we're going to do exactly what we did before. We'll draw out an axis, look to interpret the domain, sketch it all piece by piece, and join it up where appropriate. So, starting with the square root of negative x, so that's this first one up here, I know that it's everything to the left of negative 1. And in fact, the good news is I've already found that endpoint because I was asked to evaluate f of negative 1. So I know that we've got the point negative 1, positive 1, which is up here. I know that it includes that value, so it's a closed endpoint, and because it's reflected in the y direction, the square root function will look like this. Our next graph is 2 minus x squared. We might think of this as negative x squared plus 2. So a reflected parabola that's jumped up 2. Now, I've already found f of 0. So the good news is for this graph here, I've already found the y-intercept, and that's at 2. So we've got the value 0, 2. I know that it's a reflected parabola, so it's going to look something like this, and it's in between the points -1 and 1. Well, if we subbed in -1 into 2 minus x squared, I'd get 2 minus -1 squared, which is 2 minus 1, which is 1. So the good news is that it joins up neatly. So here's -1, 1. Also, if I subbed in +1, I'd get the same y value, and so we can see we've got 1, 1 as well. Finally, we've got the graph of square root of x plus 1. So this is going to be something that looks like that. It's been shifted up 1 unit. And importantly here, we need to sub in the value 1 to see where we start from. So we've got the square root of 1 plus 1. So this now is going to start at the y value 2. So I need to change my endpoints. At the end of that parabola, we should have an open dot at 1, 1. That's because in our domain, this doesn't include the value of 1. We have a closed dot now at the point 1, 2, that's up here, 1, 2, and that's going to shoot off in that direction. Now, we're asked in part C, actually before we move on, we better label everything. So here's x, here's y, this is y equals f of x, and in part C, we're asked state any value of x for which the function is not continuous. Now, as long as I can train my pen along here without lifting it off, then it's continuous. What I can see here, though, is that as I get to the value 1, and here's the endpoint, starting again, I'd have to lift my pen off the page. So there's that kind of disconnect here. So it's important that I know that it's not continuous at this point. So what value of x is the function not continuous? Where x equals 1. It's also asked me to state the domain and range. Well, looking at the domain, I certainly can find f of 1. The answer there is 2. It's this point here. So it's not that it doesn't exist at that point, it's that it's not continuous. But in fact, if I look at this, the domain is reals. There's no area of this axis where the graph doesn't exist at all. And so I would say that the domain of f is equal to reals. The range is a little bit trickier. The lowest value we can see is at this point, -1, 1. It's not over here because that is not inclusive of that point. And so I do know, though, that from this point here, that's where I'm reading it from, the lowest value for y, so the least value of the range, is going to be 1. These graphs, although they certainly flatten out, they do go off to infinity. And so we know that our top end of the range will still be infinity. So this is one of the more complicated questions to do with hybrid functions, where it does more than just ask you to sketch the graph. It might ask you to evaluate certain points, or state things about the function, either continuity or perhaps, when we do it a bit later, differentiability. And it might also ask you to do the domain and the range. Now, the second part to this video, we're going to have a look at the sum and difference of functions. And there's a few things to remember. Most importantly, if we're adding or subtracting functions, so the sum or the difference, we need to know that these functions only exist over a shared domain. So we could write f of x plus g of x, so we could write something like this as f plus g x. They're the same. But what's important, regardless of what f's domain was, and regardless of what g's domain was, the sum is going to be the intersection of both. Think of this as the overlap. The difference is exactly the same, and we need to know that it's only the overlap in which they exist. A product of a function shares the same property that if h is defined as f times g, then h, that f times g, has to only exist on the shared domain. It just can be notated a number of ways. So let's have a look at example 5, and we'll put this into a more practical context. Suppose we were asked, now I'll just fix the screen for a moment, to find f of x and g of x, find the following and state their domain. So we've got to find f plus g. So there's two parts to this question. We need to find f plus g, and we need to state the domain. I know that f of x is this graph and g of x is that graph. So finding f plus g is really simple. F plus g of x, so I might even put that in brackets, is equal to f of x plus g of x. In other words, it's just the square root of x minus 1 plus the square root of 3 minus x. The domain here is actually a much harder part of this question, and we can find this by drawing out a number line. So let's start with this number line, and we'll propose that we've got 0, 1, 2, 3, 4, negative 1, negative 2, negative 3. That should do us. Now, x minus 1. This is the inside part of f. Remember that we can't have the square root of a negative number. And so that inside part, that x minus 1, whoops, sorry about that, that x minus 1 has to be greater than or equal to 0. And so I find that x has to be greater than or equal to 1. So my domain of f is going to be 1 onwards. My domain of g is tasking me with finding this 3 minus x, provided it's greater than or equal to 0. Because again, I can't have the square root of a negative number. So 3 minus x has to be greater than or equal to 0. If I bring the 3 over, or it might be easier to bring the x over here, and say 3 is greater than or equal to x. Now if I flip that around, so I've got x on the left-hand side, x is less than or equal to 3. And so I see that here, it's in the opposite direction. So what's the overlap? Well, the overlap occurs between 1 and 3. So if I'm asked to state the domain, well, the domain of f plus g is only equal to 1 to 3. So that's an important property of the sum and difference of functions. If this was f minus g, it would be exactly the same. The domain would be 1 to 3 because it needs to be that intersection or that shared domain. Our last challenge for this video is to see if you can answer the following question. So I'll zoom in on it so you can see it a little bit clearer. There we go. Pause the video, give these questions a go, and you'll see the solution in a moment. Okay, looking at part A, we're asked to form the rule for f plus g, state the domain, and sketch the graph. So it's a really complete question here. Well, let's start by forming the rule. Remember that f plus g of x is just going to be that function plus that function. So it's a square root of 4 plus x plus the square root of 4 minus x. So there's our first mark, quite easily gotten. The domain is going to be a little trickier, but we can just imagine this number line and think, okay, well, where is x plus 4 greater than 0? Where's this bit here? X plus 4 greater than 0? Well, that's wherever x is greater than -4. Remember that this could be equal to, because we can have the square root of 0. So that's going to be from -4 onwards. 4 minus x, on the other hand, is going to be the opposite. 4 minus x has got to be bigger than or equal to 0. 4 is therefore the biggest value that x can take. So that's going to be this way. And so we can see our shared domain, and we could say that the domain of f plus g is equal to -4 to 4. The final part of this is to sketch the graph. Now, fortunately, sketching a graph like this is not something you'd be required to do tech-free. So simply by putting it into my calculator and adjusting the window, we can see what the graph looks like. So it's going to have two endpoints here. It's going to go up in an arc and then come down. Now, the trick here is going to be thinking, well, what's that maximum value? And of course that occurs where x equals 0. So 4 plus 0 and 4 minus 0 will give me the square root of 4 plus the square root of 4, which is just going to be 0, 4. The two endpoints here, well, they're going to occur where x equals -4 and where x equals 4. So I can just find these by subbing them in. We'll start with the first one. 4 take away 4 is 0, so that's going to be 0. And 4 minus a negative is going to be 4 plus 4, so it's a square root of 8, or 2 root 2. Likewise, when I sub in +4, I get the same thing, 2 root 2. You can use your CAS to help you out there. Finally, we might go x, y, and y equals f plus g. So we've labelled all our endpoints, we've got our shape accurate, and we've got our critical points like the y-intercept labelled as well. The second part to this question, part B, asks us to find the product function fg. So the product function is just going to be fg of x is the square root of 4 plus x times the square root of 4 minus x. Now, we can think of this as 4 plus x times 4 minus x, all to the power of a half. So we'll just give ourselves a little bit more room to work. And that's the difference of two squares, so that's 16 minus x squared. So this is the square root of 16 minus x squared. Now, that's important. It's going to help us with our domain. But of course, we already know our domain. The domain of f plus g is the same as the domain of f times g. It's the same as the domain of f minus g. So the second part to this question is as simple as saying dom fg is equal to -4 to 4. The more difficult concept is trying to find the range. Fortunately, we'll use our calculator again to help us with this. So bringing in my class pad, I know that this time that plus is going to be a times, and we can sketch the graph. We can see here that it goes up to 4 and it intersects at 0. So my range, if I get rid of that, of fg is going to be 0 to 4. So there's a couple of things we should look to in summary. If we've got the sum, difference, or product of functions, then their domain is always defined as the intersection of each. That's the most important part to remember. Most of these will be tech active, but they might ask things that are difficult for your calculator to instantly answer, such as the domain, the range, or explaining why it does or doesn't exist.